So this is the second year I've been here, and I decided to up the ante and bring in something that probably doesn't show up in computer network conferences very often, which is some stuff in chemistry. And so overall, since the slides were posted in advance, I won't spend too much time on the overview. But basically what we're going for is an entirely new way to consider flow control in networks using what nature's already given us. That's basically summing it up. So there'll be some background. I don't expect anyone to have either a math or a chemistry background. That's not fair. So I'll do a little bit of relevant background in chemical kinetics. The formal model of how we can translate some of these ideas in chemical kinetics to packet flow in a network. And then some actual applications. This is in general, it's a lit review of a lot of different things that have been done in both the networking space out of some Danish researchers, as well as we'll briefly mention some stuff that's done in the chemical physics and physical chemistry realm and some of the mathematics realms. So it's kind of a comprehensive lit review on what can be done with a lot of these ideas and how they can merge and end up straight in engineering. So some of these applications I'll talk about have actually been implemented, and admittedly in an academic sense, but they have been implemented. There is code, it exists, it's real. So unlike my last year's talk, which was all theory, this is actually a little more real. And then I'll discuss some limitations and future directions I'm taking with it as well. So, the first thing is, what is a mathematician doing talking about chemistry to network engineers? Wait, why am I here? So I believe pretty strongly, in whatever cliches you want. Don't reinvent the wheel, work smarter, not harder, all that stuff. When we make airplanes, we study flight, and we study flight that occurs naturally. You study it in birds, you study it in insects, you study even UAVs and drone stuff. Now we're studying insects and how they swarm. We look at what's actually been given to us and try to understand how we can make use of that and the things that we can build from the ground up. Like computer networks are completely artificial. We created them from the ground up. So let's try to exploit what work nature's already done for us. And that actually comes in chemistry. So what's really nice is that packet flow in a network has an absolutely beautiful analog living inside reaction mechanisms in chemical kinetics. And picture things, it may look a little different, but if I have a big jar and I just pour a whole bunch of chemicals in it and they start reacting, there's a whole bunch of different pathways that are happening, especially if I take one chemical, put it in with two others, and each of those two others want to react with that first chemical and do something else. What's going to govern what molecule gets pulled into reaction 1 versus reaction 2? Why does it precipitate out? Why do these reactions end up the way they do? We have mathematics to describe all that. And a lot of these things just happen in nature. Sometimes you throw enzymes but these things happen in nature. They just happen. We don't, there's nobody sitting up there with a control panel scheduling these events. They happen. So why? So we'll actually go over some of the mathematics of why. Like particles or molecules, there's ways to study these, right? We can have microscopic or quantum behavior if you're interested in physics. That's where the stochastic analysis comes in. But you can also have macroscopic dynamics. A chemical engineer working at scale in a factory isn't quite as concerned with microscopic interactions so much as the macroscopic dynamics of giant vats. So the nice thing that we're going to take advantage of is that chemists, physicists, and mathematicians have worked out have done a really good job working on all of those levels of possible analysis that you can exploit for your networks without having to reinvent the wheel. We just have to find the right analog. So currently, what we notice are issues if you're trying to scale from microscopic, which is generally more accurate, right? If you want a fully accurate picture of what's going on, you dive all the way down past where things look smooth, down to a microscopic or even quantum level. Now the problem is, even modeling something on a quantum level for a single molecule, understanding even what a single molecule's electrons are doing is extremely difficult. More accurate, but difficult. It becomes intractable if I want to say, give me the quantum behavior of every molecule in a giant vat. That's impossible. So one way we have dealt with it in the past is to smooth it away. I take those random fluctuations and I smooth them away with differential equations. That comes at an extremely steep cost. So my interest in some of this research is to find where that middle ground is, right? How much of that random fluctuation can we deal with while not getting so far in the weeds that we've become completely computationally intractable. So take an example. Even if you're looking at your own network and packet flow, one thing that I notice happens an awful lot is a tendency to over smooth something. We just go with steady state traffic and just let things flow. But what happens when you smooth things too much is when you get a random fluctuation or a huge spike in traffic, if it's enough of a shock to the system, your system's going to crash. It doesn't matter if it's a mechanical system, it's a lightning strike, or it's an extra packet that just is going to tip everything over the edge. So how do you analyze something while allowing for the existence of these random fluctuations without getting obsessed with equations we simply cannot compute? So we'll be talking a little bit about some of these ideas and what has been done in the chemistry and physics literature. All right, so we're going to discuss, there's only one real equation we're going to care about, and it's one called the law of mass action in chemical kinetics, and we're going to use that to create what's called an artificial packet chemistry. This is a theoretical model to analyze packets in the same terms that we would analyze molecules in chemistry that allowed chemists to build computational models of reactions. And we're going to note current applications of this model, not just ones in chemistry, but I mean literally ones in a computer network, and then discuss some of the limitations for transferring this over to the networking space. There are some limitations, there are some assumptions that are a little bit too strong, and what we can do about it in the future. So with some brief background, I promise a couple of chemistry equations and a few math equations, but it won't be too bad. So if we have a chemical reaction, think back to your high school chemistry, with some number of reactants, A through M, and those reactants work together and they make some kind of products, say B1 through Bn, then that's how we can simply express a chemical reaction. For those of you with a chemistry background, we are only considering forward reactions, no equilibrium or backward reactions, because packets if they flow backward, we're gonna have another link. So no equilibrium here, no equilibrium reactions, just forward reactions. So for an example, we have hydrochloric acid and sodium hydroxide, an extremely strong acid and an extremely strong base. Acids and bases always mix to form salts and water. So in this case, they will mix to form simple table salt and water. This is a strong acid and a strong base, that plus lots of heat. It's a very exothermic reaction, which is why if you're burned by strong acid, do not dilute with base. You will make the burn worse because it's exothermic. Dilute with weak acid and then water and then base to cleanse it. I've had enough lab accidents to know. Okay, so that's the simplest, one of the simplest forward reactions. So this is a way to make literal salt water by diluting a strong acid with a strong base. Okay, in a very simple reaction, if we just have one reactant going to one product, and this may be, for the sake of argument, something like a decomposition reaction. Some chemicals may decompose, have a half-life, and you may lose a molecule and go to a gaseous form, or some other thing like that. The rate that this reaction occurs is a really nice differential equation in terms of the concentration of the reactant. And even if you don't like differential equations, we're gonna let that C sub A be the concentration of the reactant. So you can measure that however you like. Typically chemists measure it in moles per liter, but you can measure it however you like. We might do packets per link, but however we wanna do that. Put simply, the rate at which the reactant disappears is proportional to the current concentration. So the higher the concentration is currently, the faster we're going to be moving to product. The reactant will disappear. I can flip this the other way and write this in terms of product. The rate of creation of the product is proportional to the current rate or the current concentration of the reactant. You can take whichever you want, right? It's just an analog. We make one reactant, one product. That is the law of mass action for just a unimolecular, nice, simple unimolecular reaction. That's all this guy is. So if we have multiple reactants, like my hydrochloric acid and my sodium hydroxide, then we can say that the rate of a forward reaction is proportional, there's some multiplicative constant in front, but it's proportional to the concentrations of all the reactants, and that's what I have. That is the law of mass action, and that's the concept we're going to use. Now the differential equation that's formed out of this gets a little gross, so I'm leaving the diffie-q's off here. All we really care about is this principle for now, right? We're kind of leaving most of the math out of this. So all we need to really understand is that the rate of a reaction is proportional to the concentrations of our current reactants. How do we move that into a queue with packets in it, or a buffer with packets in it? So on the left, I have a queue, and those queues have packets or something waiting for them to process. And on the right, we have essentially a two set of unimolecular reactions. And what I've done is I've messed some things up. So what we have, I've labeled the QX, that's the queue, and it fills up with packets. Packets come into QX at rate lambda 1. They are serviced by that server that I'm labeling K1, and K1 is my proportionality constant. Now, what you notice about reaction 1, that K1, is it actually, to occur, it needs to pull a packet from X and a packet from Y to occur, or the event cannot fire. Whereas reaction number 2 just needs something from Y. So what we're actually saying, and we'll go over some of the terms. So that lambda I is the inflow, what we would call the arrival rate. It's the average arrival rate, an average number of packets coming in. Or on the right, the chemical analog is the average rate of molecules coming in. The mu I here, that's your service rate. On average, how fast are we servicing these packets? That nu I is just the reaction rate, so that's me separating Qs and chemistry here, but they ultimately stand for the same analogous thing. That C sub X and C sub Y are concentrations if we're talking about chemistry, or fill levels if we're talking about the Q. Now what we notice is that with this system, these reactions are coupled. The second one requires Y. The first one also requires Y to fire. So if there's only one packet sitting inside of Y, which reaction fires? Does it go through 2, or does one pull it first? Which event should get scheduled first? So when you have coupled reactions, either in chemistry or in your network, when you need things from 2 different sources to fire, this can make analysis and scheduling very complicated due to the coordination that's required. So you can try to do it by hand. It's kind of a pain, but let's try not to do that. If this were in a vat, if I put chemical X and chemical Y in a vat, and these reactions needed to occur, this would sort themselves out due to the law of mass action. We don't have to go and actually make these reactions happen. They sort themselves out. I'd like to pause briefly for those that are a little more interested in the specifics. There are some assumptions that I've been implicitly making thus far. What I have done is actually broken a couple of rules that typically show up in networks. And the first one is that we're actually working with a non-work conservation policy. Typically, when we look at queuing theory, we assume that if there's something waiting in the queue, we're going to serve it. We don't let something sit in line and your server stay idle, or whatever's processing your packet stay idle. In this case, we are going to allow for that. Even if the queue contains packets, we may allow the server to stay idle here, and from a load balancing perspective, this will turn out to be better. The other thing, for those that are interested in queuing, is that for mathematical analysis, it's noteworthy that this analog so far, working on it, is only good for the simplest type of queuing model that we have. That's what an MM1 queue is. It's the simplest type of queue. If you've seen any queuing books in networking, this is pretty much the one that they stick with. Since I only have 30 minutes, I'm not able to go into the queuing theory background, but I'm happy to talk about it. The queuing discipline is first in, first out. No processor sharing, no service in random order. So again, the other thing that I think is the most important one to bring up is that we are ultimately in equilibrium, or the steady state. So we are assuming that the network has been on for a very long time, and we've kind of settled on what our typical behavior looks like. The reason for this is that non-steady state queuing analysis is extremely difficult, to the point where it's almost intractable. It's a pretty huge problem. And moreover, the law of mass action actually only applies to what we would call an equilibrium state of reactions. Okay, so what is actually being accomplished with the law of mass action? We have natural synchronization in scheduling. No actual human interference or any interference is necessary. It just sorts itself. We have the ability to handle competing servers that are competing for the same packets in a queue. And we have indirect communication between 2 servers via the fill level of the buffer. We don't have to send messages back and forth saying what's going on, what's your next event. All they have to know is what the fill levels of all the different queues that they need to pull from are. There's no communication necessary between these 2 servers. Reactions don't need to communicate, neither do servers. Why should they? All right. So here is an actual example of how you might kind of schedule this, and this is setting us up for defining a formal model here. This is a law of mass action competitor to the push-sum protocol. If we had a work conservation policy here, where we basically process packets as soon as they arrive in a queue, you would end up with a bottleneck at that node 2, that N2 square that you see there. Non-work conservation allows for what our goal is, and we'll talk about in the application, to be achieved, is to calculate an average by simply letting this system settle to its steady state and the average fill level will give you an average calculation. There is no symbolic computation. The result for calculating an average can actually emerge from dynamic interaction of packet flow that is allowed to settle. So now what is it? How do we actually move from a physical reaction to an artificial packet chemistry? So this is a mathematical definition, and we'll go through an actual example too. We have 4 components, and I'll go through each of those components with an example to clarify as well. The first one is the graph that represents the computer network nodes. A graph consists of a set of vertices or nodes and a set of edges or links. And we assume that these links are unidirectional, by the way, so if I want bidirectional flow, I need to have a parallel edge for links. We're also going to list queue instances inside a node. What I'm actually allowing is that inside of a box, I'm going to allow for multiple buffers. There's not just one buffer per box, I can have multiple ones. This is going to be analogous to what we would consider molecular species in a vat. So if I can have 18 different types of molecules laying in this vat, that's the same thing as saying we're in this network node, we're going to allow for 18 different buffers. This can also be used, by the way, if you're interested in priority or class-based traffic, you can actually extend this analog to class-based traffic. Simply have a virtual queue for each class, and you can use the same concept. The flow relations that are analogous to reaction rules are going to give us flow relations, and we'll go through an example. And A is our reaction algorithm, which all we care about is the law of mass action is what governs this system. So let's take that example from before. I have 4 nodes, N1, N2, N3, and N4. So those are the boxes that you see up there. Each node has a bidirectional link with all that are adjacent to it. So my edge set, for instance, first one is N1, N2, but because I need to go back, N2 to N1 also is another link. And same with 2 to 3, 3 to 2, and so forth. So you can see where my vertex and edge set are defined. I have 4 queues, or 4 molecular species, whichever you'd prefer to think of it as, 1, 2, 3, and 4. And these are simple unimolecular reactions. I'm just sending from species A to species B for any 2 that are in adjacent edges. So X1 to X2 is one reaction rule, X3 to X4 is another reaction rule, etc. And this is just the law of mass action that's going to govern how this system operates. So this is just me taking everything that we've already kind of gotten used to and putting it in a formal mathematical definition I can use. Now, since it's only a 30-minute talk, I can't go through all of the formal analysis techniques that this analogy has now opened up to us, but there are lots. Ooh, okay. The first one, so we'll go through these pretty quickly. Since there's only 10 minutes left, there are a lot of formal analysis techniques, anything from a chemical master equation to fluid approximation, Kirchhoff's current law, if you're interested in signal and control theory approaches or general stability analysis. The point is there is a massive wealth of things that are available to us now. Okay, I'll only probably have time to go through a couple of applications. So the first one is how we actually implement a scheduler. Each network node has its own scheduler to compute the next occurrence time of each reaction in its local node. It's going to sort these events into a priority queue and then execute when the first event occurs. The difficulty of this problem is to dynamically react and schedule things as packets come and go. This implementation has been done. It's done by the next reaction method in O of n log n time, so it's actually really efficient. The rate constants and fill levels are going to drive the ordering of events. There's no timestamp tagging required. The service rate is proportional to the fill level of all of its dependent queues. Any interleaving and dynamic scheduling are automatic, and it's the same way that exothermic chemical reactions happen. That's one application. Second one, we can implement a chemical control plane. So instead of sending packets through a complex queuing network physically to shape packet flow, we can create a flow plane that handles flow control. And at this point, we can actually introduce what are called virtual enzymes to control that rate, just the same way that your body does when it's controlling the rate of reactions via enzymes. And there's an awful lot of mathematics to handle that. One other interesting one that might be of particular interest is dynamic cell sorting via a fraglets language that has actually been used to program a physical packet network. This language actually exists. Each packet is a string called a fraglet that contains instructions and data. It self-sorts into queues, and it's tightly coupled with mathematical models and analysis, so you can actually use any formal verification type theories to actually handle analyzing your code. The next one is congestion control. So this one, I think with the timing, I won't be able to go through this in detail, but what this actually allows is via a combination of the law of mass action and enzymatic reactions, we are able to make a chemical equivalent to TCP-ReNO, where the transmission rate is actually controlled by an enzyme whose creation itself is controlled by the rate of lost packets. So the more packets you're losing, we want to slow down that transmission rate. So this mathematical model actually generalizes really nicely to something very real. Now, unfortunately, there are a lot of limitations to a lot of these applications. The first one is that all these models thus far have assumed infinite queuing capacity, which we all know is not very realistic. We have finite buffers. How do we handle that? I'll tell you hopefully next year. I'll tell you next year. So the first one, that the true link is that simple queuing type behavior called an MM1Q in steady state. And as a mathematician who does specialize in queuing theory, it's too simplistic a model. For one, it can't handle any deterministic service rates, so that changes the queuing model. And I'm not entirely sure that analog still holds exactly, or it would need adjustment. If you're wanting to deal with more general distributions, or worse, you might have when the packets arrive, if we assume that when each packet arrives, the time between their arrivals is independent of each other, how many people think that's actually a realistic assumption? Lots of head shaking. That's not realistic at all. There is no mathematical model that can handle that yet. So when it was mentioned that I do research in sequences of dependent random variables, that was one of my primary motivations to look into that. No queuing theory model can handle dependent arrivals. And there's lots of reasons for that, but that's one of the things that I look into because it's not a realistic assumption. We need to actually look at what's reality. So what are future directions for this? I know this has been a very, very brief overview, but what I would like to see, the downside with the lit review that I did do, when they did actually apply some of these ideas to computer networks, all they really did was mention the analysis techniques open. I have not seen any actual analysis of the dynamics of what maybe, say, a scheduler on a torus network might be like under this model, or a butterfly, or any other typical networking model using something like the chemical master equation or other stochastic dynamic tools. So one thing is to understand, can we understand actual dynamics of packet flow better and at a much smaller, more microscopic scale than we could before? For those of you that are interested in the more advanced mathematics, there's a very, it looks abstract and it looks ridiculous, frankly, but it's actually very useful, something called a Petri net model for more complex networks. The more nodes that I put in and the more reactions and links and dependencies I have, if I'm trying to understand how these things fire and when they fire and what is considered reachable, what state of the network is considered reachable from another state, is it possible for me to send packets from point A to point B and C at the same, either at the same time, or if I have to do it in order, which order should I do it in? Does it matter? This Petri net model actually allows you to figure out mathematically if these things are what we would call commutative, if the order actually matters. Obviously, the finite capacity buffers are something we need to look into. And I mentioned the generalized models and heavy traffic perturbation. That's one thing I'm really interested in, is breaking things. I want to break your network. I'm interested in network resilience. So if I perturb one of these, even an artificial packet chemistry in steady state, how stable is that? Have I completely just thrown it off the rails and thrown your network dynamics off? Or as an analog, have I thrown the chemistry completely off by perturbing it by, I don't know, adding pressure or shaking it or whatever? And then obviously I would want full implementation of some of these reaction designs to facilitate other protocols than just the TCP-ReNO that's been done in the literature. So is there a chemical analog to a lot of other networking protocols that might be easier to analyze? So in a conclusion, thank you for going with a very lateral thinking injection to a heavily network engineering conference. I think this kind of interdisciplinary research is filled with potential. There's so much work being done across so many different disciplines, and all that really we need is to find the right mapping or the right analogy, which is what I try to do for a living. The potential, this has all come out, all this literature is no more than about 7 years old, so this is all very new. But I think it's a huge testament to the value of interdisciplinary and academic collaboration with the private sector. Me as an academic, I've been in the academic sector, I've been in the private sector, now I'm on my own, and the best work I think I've ever done has been private sector collaboration, right? Most of the time, if you're in an academic setting, we have a tendency to shut our office door and pretend like any other department but ours doesn't exist, and that's how you end up with these massive gulfs between departments, let alone between the private and academic sector. So hopefully this was at least entertaining, if nothing else. But I'll go ahead and open it up to questions. I realize that was really brief, so I'm happy to talk about some of the details afterwards, but any general questions that you might have in the remaining time we have.